I know why it has to be negative. I think I know why it has to be negative. I've been just having a bit of a doing a bit of thinking about this in between now and the last video because I didn't make it to record something in between. And basically, let me show you why I think I know. um, might be totally wrong, of course. But I mean, it kept me thinking about the fact that the x and the p quadratures will be the equivalent. I mean, not the equivalent, but like sort of intuitively, you have different observables as well. In the same it's with the discrete quantum computer, you have the z, the x, and the y observables. And Grove's algorithm is kind of working in between the z and the x observables. So you're basically um, wait a second, is it? Because essentially you're phasing by 180 degrees your solution. That's what the oracle does. And wouldn't that be the y observable? Is the y observable the phase observable? What is the y observable? That's just out of probably going a bit of on a tangent here, but anyway, it's whatever. It's in between two observables, right? It's not important. I don't want to waste my time on this right now, but basically, so what I find cool about this is that when you measure so the quadratures, and by the way, this is something that I remember now from Jack's Cerrone's from Jack's original. I just can't remember his blog. Is it a GitHub thing? I think it's this, but so that's me not bookmarking things properly. Now I'm at his blog, um, and there's the QAOA blog post, which is then turned into the notebook that he shared. But basically, that's one of the things he starts here with these. And by the way, Jack, I think you have got a mistake here because you say you. Oh no, you're not. You haven't got a mistake actually, because your first step is basically these here. So it's not just the initial preparation, because the squeeze gate is supposed to prepare. Because here I was like, oh wait a second, but the thing that's spread out here is it's kind of the p observable, not the x. Mm. So how am I supposed to drink coffee without hurting the microphone here? But I see that your first step is done. So that Z, P, and R already um, take you there, I guess. But it's interesting. Okay. Anyway, I took that as a so as a I basically copied that from you. Okay. So if you squeeze it like these, then what you're gonna get is so if you squeeze it like this, then and I give it a go, then you're gonna get something like that, which is, let's say, okay. Um, and now I realize that really when I was in the previous video, I was trying to basically build I was trying to build the cost function in the x quadrature, but I think that's because I maybe a bit too focused with the fact that it has to be that I'm talking about the cost and Hamiltonian thinking, because the way this makes more sense to me is like I should be building it on the p quadrature, right? Um, because that's kind of the premise of the whole algorithm is like if you're able in one of the observables, if you have an oracle that is that is able to basically flag the element that you're looking for in one of the uh, in hmm, in an equal superposition, right? Because the equivalent of an equal superposition here would be that you've got that flat kind of flatty distribution, right? And so the way that you flag it in Quark I'm gonna open the Grover search here. So the way that you do this here is by having that oracle, which is basically a control Z. So and kind of that's the cheating, so to say, for the sake of the example. You know what you're flagging. The assumption is you have that, you've got that as a given, right? That's the oracle is there. There's a mechanism to flag the element, and then you're doing the different operations that here, because of what Craig is using here, you don't see the Hadamarts, but there's a Hadamard hidden inside here. So what you're doing is you're kind of like exchanging information between the two different observables. We'll get to that at some point, but uh, and if you go here, what I found in the quantum operator definitions dun, 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 is that actually, if I go to the Fourier, which is what I think seems to behave a lot like the Hadamard gates. Why there's no Fourier in here? Or where did I find that? I found a gate that basically does x equals minus p. Oh, here, the free. Okay. Ah, because it's a special case of the rotation, and maybe that's why Jack, where are you, Jack, has, because he's using a rotation, and that's maybe why Jack has that as the first step, because basically the quadratures have been exchanged after applying those first operations, which include a rotation, by the way. So you've got that x equals minus p, and I think that's why you gotta. So that's why Guillaume says you're gonna have a cost function which is the negative of the thing Gaussian centered at the point to be found, because basically when you will be exchanging the information between that, the sign will change. I might be totally off, but that's intuitively what I think that might happen here. So, because when is it? Yeah, exactly. You will apply that to the position, and you'll basically exchange. Yeah. But then okay, no, minus p exactly. Yeah. And then you'll need to apply the oracle again in p. Let's. So, but basically we got our starting state in here. Yeah? Um, but it's not really the starting state that you really want, because your starting state. Because I'm hesitant to use displacements within the actual Grover algorithm. Because if I use displacements, then it's not going to work, right? I mean, if I have displacements as part of my oracle, it's not going to really work. Because then I'm going to keep displacing, sort of accumulating a displacement of the x quadrature every time, or the p quadrature, like. And if I take a look at this, there is a displacement happening in this example, and the only gates that are being used are the Z, the P, and the R. The R is a rotation, and the Z and the P, what are those things? So the Z gate, definitions, squeezing, no, rotation with the R, P, the quadratic phase is a P. What is it doing? It's using the P, P and Z, quadratic phase. It shares the phase space, preserving position. Ah, look at this. Huh. That actually adds a displacement to P, preserving position. And that's what you want intuitively. Aha! I don't know, it looks like it's the right. Oh, man, I should have. There's gonna be a way you can simplify that documentation for the people like me. So it looks like if you apply to the momentum quadrature, it's gonna add, it's gonna displace. It's gonna add to that quadrature, but not touching the x quadrature. So that's good because then it means that if we think about our oracle acting only on the p quadrature, um, that kind of makes sense. Interesting. Let's see how does this work. So if I use the p, the p is the p gate quadratic phase p gate. How can I parameterize that? So this is the parameter s, I guess, which is amplifying that movement. The problem is that if x is centered in 0, I don't know if this is going to really do anything, right? So if I say, for example, 3, what is it going to do? That's not what I want. If I do minus 0.5, but it does touch the position quadrature. It does something weird. It's like it flattens the thing. It flattens the top. Let's try without the squeezing gate. I just want to make sure that there's nothing here wrong. Let's clear all. I want the quadratures. The empty circuit is that. Because I might have to do the P first, right? Jack does, what is it? Jack does the rotation at the N. Then there's the Z. I'll end up probably copying him, I already see that. But it's been actually quite a... So the P, what does the P do? So if I do this and now I do 3. That doesn't displace it, but then I'm reading this wrong. This gate can be decomposed as P plus S times X. Well, yeah, X is, yeah, I mean, sure, S is just the, so X is actually, so it's actually adding the two things. It's not a value that you're adding, you're adding the waves, or that's why you're getting something like that. It's not technically displacement, so, sucks. Kinda sucks. What is the, let's move on. What is the Z gate? Cubic phase. Is this the actual traditional Z gate? Like phase gate? States, operators. Why isn't it there? Z gate. Momentum disp. Oh. Oh god. That actually has a momentum displacement. Okay. Oh. Yeah. Which kind of makes sense, is what I was gonna saying, is basically what you're gonna have to, in combination with the Fourier gate, it's gonna do what we want, I guess. So let's do it again. So it's a momentum displacement. So if I do this, and what's the parameter is just, so if I gonna, and maybe it doesn't make sense that it's called a Z gate because it's actually displacing the one quadrature, so you're adding a relative phase between momentum and position. Maybe that's the, so what if I do this? Yeah, but it's disturbing a lot. Maybe that's why you then need to correct with the with the P gate, but I can't seem to displace it far enough. What if I do something like this? Just trying different values because I don't know how this is gonna. Oh, that's like okay. That's like a neat. But I want it to be minus. Isn't it that you can't do that? No, you can't do that. Yeah, but it's not 0.5. That's not what you want, right? Is there something off with this? Go 0.5. No. 0.9. The farther you go, the more you're distorting the thing here. Because if I now I add 1.5, that already starts to look flaky here. Okay, so this is the position is okay. And is it possible that the quadratic phase would help me correct that? Kind of not, right? Because it. Oh, but wait a second. We saw that it somehow flattened X, or it smoothened X somehow. Let me go be more like. Let me just go to 2. Okay, so now it's kind of already like in bad shape. But maybe at the end of the day, maybe we just don't care. I mean, all we want is that, right? So. So if I add a P gate of say 3, what is it doing? So, ugh, if it has actually not done, it has actually flipped the stuff, rotated too much probably because it's a rotation, right? It shares. I mean, it's not a rotation at all. Doesn't exchange anything. 0.5. Yeah, that's okay. Smoothens it up a little bit. Interesting. Interesting. It does actually touch, but you see, that's the funny thing. It's like I thought this is not supposed to affect the X quadrature. Hmm. But it does. If I do this, okay. I don't know, just trying to run the values, see what's really happening. But anyway, so why am I doing all these? Um, I lost my thing here. So um, so basically, um, you've got the initial state, which is, so we said it's just a squeezed. It's just a. Oh, what if I do 3? Doesn't seem to move significantly farther. 9. Boah. Why I can't displace it as far away as I want it? Kinda sucks. Because this is supposed to be a momentum displacement. This position displacement. Okay. Anyway, so this is the initial state we wanna start with, because it's basically a kind of flatter distribution here. What we want the oracle to do, we want the oracle to basically on the p quadrature um, on the p quadrature it needs to have the negative spike around the number that we want to find as least as possible. And this is kind of the cost operator, so to say, the cost operator, right? And then with the Fourier transform, which is special case of the rotation, we're going to exchange those things like these. Okay. The way that you want to do that, probably, my intuition is telling me that you want to do the stuff. So you actually want to do the cost of, now that I see that, you want to do, wait a second, so you want to do the, yeah, you want to do the cost function on applied on the x quadrature and then apply Fourier transform, because when you will apply Fourier transform, because this allows you, I think this allows you to have that displacement in there without really accumulating it. Let's see if I'm explaining myself correctly. So I'm going to leave that Q mode in here. I'm going to move to mode to the Q mode 1, to mode 1. So if I do a position displacement, right, of 3, was that working actually? Yeah, kind of. Let's say, like, I'm not going to worry about displacing it exactly to 3, because it's too much complicated right now. Sorry, I'll just clear all. Maybe I had to reset the H value actually. If I do a position displacement of 3, maybe that's the reason. Quadratures. Yeah. Good. So I have this in here, but I probably want to squeeze it a little bit more. So I'm going to squeeze that a little bit more by, I don't know, I have no idea. The other way around, I think I had to squeeze it first for some reason. Clear all. But is it clear? That's not clear in the settings. Okay, that's good. So we start with these quadratures. Okay, it is actually squeezed indeed. If I squeeze it a little bit, let's say 3. A little bit. It's not a little bit. Okay, now it's squeezed, because before it was like between. Yeah. Now we're gonna displace the position by 3. There you go. So you got the displaced here. Exactly. And now I should apply Fourier transform, because basically I want to have that. I want to have that in my momentum. The reason why is that why is that? Why is that? Because at the end, what I'm going to measure is the position. That's where I want to find the result. So, and again, and that's an oracle. So I know it's kind of cheating, because I'm doing what I'm not supposed to know, right? So if I apply Fourier transform, we've literally flipped the quadratures. I still don't get it why. Maybe I'm bad at the maths, but this is supposed to be sort of x equals minus p. Maybe it's just bad at the maths. I gotta have to recap what it really means to have the negative of a function. I'm sorry, Guillaume. You're probably laughing. It's the negative of a thing Gaussian center at the point to be found. Yeah. Anyway, and actually we got a. Yeah. Anyway, so but these three operations, how can I like? Should probably keep them. Let me add some modes. So basically, these three operations, they all make the oracle, right? Or in this case, I would say the cost Hamiltonian, right? And now what? What's next? Because or is it that the oracle is just a squeezing and the momentum displacement, really, and that's already your mixer, because that's what the mixer is doing, right? It's so if you start, I'm gonna put those things in here, so I just have them as a reference. We're gonna work with QMOD1. If I start with the squeezing gate, that starts basically like that, okay? Mm. And what we want to do is we want to take that here, the 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 x quadrature to basically have ha, we want this to end up being something like this, around 3. That's our goal, because it means we found 3, right? um, I think 3 was the number I picked up in the last video as an example of the number you want to find. um, so if you've got your if you've and then the assumption here is I just kept to repeat I keep repeating the statement, the problem statement myself, because I want to make sure that I'm not doing something that is just not Grover, right? And that I'm just like not doing any actual algorithm or something. So that's the mechanism that and we're kind of cheating here, but that's on purpose. That's the whole point, is that this thing as an X, we can now build an insight because we know what we're looking for. But the idea is like that's the black box. Imagine you have something that basically creates that type of creates that type of of wave, right? But still, still, so here you've got the initial state, and then there's these things being applied. Okay. Here, if I now do, if I now apply this, what happens? So this is just the initial state, and here we've got the that's not what it should. No. That's not what it should. It should be everything, because we want it at the p quadrature. So if I do this now, what's gonna happen? Okay, So now we got it the P quadrature. We've applied the oracle. Now we apply a Fourier transform, and that's your mixer. Yeah, so this is remember, this is in theory a black box. You don't know how this is implemented, right? So this is just now for the sake of proving that if you have such a black box, then by applying the black box and the Fourier transform and the black box and the Fourier transform, you should get something like that. But or at least that's the claim of Guillaume's paper, right? Which is this one here. Because I think that's the point, is that Grover, was he here? Is that you've got your constant Hamiltonian, and then you basically mixer who's a projector on a state, the Charman. Okay, the mixer is just the Hadamard, the Fourier transform. Okay. And I still want to go then to the actual quantum paper, this one, quantum paper. What am I saying? I just say such a is it this one? Can't remember. I have it linked on the other video. I'll go take a look at it, because I actually then want to go to yeah, quantum search with continuous variables. Exactly, and go and take a look at this, how they build it here, and then compare what I'm kind of doing here. But that's basically it. So now if I now give it a run, interesting, because now I've got position, but it's on a -3. So that's where the plus and minuses are going. Oh my god, that's where the negative goes. Oh, I'm so stupid. Oh, I'm so stupid. I always thought the negativity would be sort of across the y the vertical axis. So then this displacement should not be. Then this should be a -3 displacement. So if I do that, now I have. Yeah, but now it's like I basically solved it already. Hmm. That's not. Hmm. What happens if I repeat that again? So if I now have another iteration of that, so I have the s in here, and this is the parameter 3. Don't remember y. Then I have an x. The x has the parameter -3, right? And I have f, which is Fourier transform. And then I have a mixer, another f, right? So I've basically repeated. This is initial state. This is black box. This is the mixer, black box, and mixer again. So it's almost centered at 3. At 3, if I do that again, is it? Yeah, I'm kind of getting the same, but is it getting smoother and smoother, or I don't think so. But the thing is, like, I was expecting that it just takes more steps, right? So that's what I'm saying. I don't really feel comfortable that that's it, because I feel I'm kind of cheating. I'm kind of cheating a lot here, because the oracle is too good, I would say, because it flags exactly what you want. But I mean, that's the case with the discrete quantum computing as well. If you've got like just a bunch of qubits, like it just takes one iteration. Like it's when you add more qubits that it takes longer, because you're basically why? Because you've got more. Why does it take longer if you have more qubits? Because you've got a bigger space. Because if I now would do a homodyne measurement, and I would go How do I know quadrature is mode 1? How do I know the result? Pos select? You can choose to pos select on a particular measurement value. But what's the result? That's where is the result? X mode 0. Hmm. Where can I see the result? I can't see the result really. Do I have to pos select or? Where can I see the result? That's so confusing. I want to see the result. Mode 0, but there's no mode 0. Anyway, that's for another time. But basically, okay. So I think I'm gonna leave it here for now. I basically for this video. So this kind of works, but I don't really feel it's fair. I don't really feel that's actually the algorithm. I don't know. It just feels like that's too good of a black box, and then the Fourier transform, man. Huh. Huh. I don't know. Is it really these? That's basically you've got now these in your position. But I mean, with one step was good enough already. So I don't know. I have to think a little bit about it. But maybe I can compare it with the discrete variable quantum computing. I don't know. Hmm. Well, I don't know. We'll see. I gotta sleep on it. Uh, that's given us the result we want. You know, assuming that we've got that box, and then we just apply the box. Start with the squeeze state, apply the box, and then put it into and then apply Fourier transform. Yeah. I don't know. Could be that's it. I don't know.